Okay, hello everyone. Today we will continue to review the exercises. Last time we have finished the fill in blank questions. Now there is some short answer questions. For example, question 1. Please write the full name of CSMACD and describe it briefly. We know CSMACD means carrier sense multiple access with condition detection. And what is carrier sense? What is multiple access? What is the meaning of condition detection? So you can describe it briefly from the textbook. Question 2. Please describe briefly the reason why Ethernet specifies the minimum valid frame length and the maximum transmission unit. There are 2 points. Ethernet specifies that the shortest length of a valid frame is the amount of data transmitted in the contention period too tall. So it can determine whether the transmission has experienced a collision before the frame transmission has been finished. Furthermore, because the collided frames are definitely shorter than the minimum frame length, it is also convenient for the receiver to ignore the collided frames by frame length. So it will make it easily to drop the collided frames for receiver, simply depending on frame length. Point 2. Why the maximum transmission unit needed? The maximum transmission unit, MTU, is specified because of limitation of memory space in the network interface. Okay, usually there is a limitation of memory space in the network interface. So the transmission unit frame should not be too large, should not be too long, right? Better delivery. The reason 2, for better delay characteristics, if the transmission unit is not limited, then when a long transmission is carried, then the delay will become worse. So for better delay characteristics, the third reason is for fairness of the data frame transmission. The fairness of transmission. So if all the stations transmitted in average length of frame, if all the stations transmit the frames with average length, then they will share good frame fairness. Okay. So the maximum transmission unit, MTU, because of limitation of memory space, better delay characteristics, and better fairness of transmission, right? So then we have some comprehensive calculation. We have calculation application and application questions. Question 1, assume that in CSMACD Ethernet, the distance between station A and B is 4 kilometers. The propagation speed of the signal is 2 times 10^8 meters per second. Data rate is 100 megabps. And station A sends a frame earlier than B, a little earlier than B. Then collision occurs. Please determine. 1. How long does it take? As soon as possible for station A to detect collision. How long does it take for station A at latest to detect collision? Question B, if the distance between station A and B is shortened to 2 kilometers, what should the minimum frame size be for this Ethernet? So it is not very complex. I will analyze it. One way, if we know the distance between the longest distance between station A and B is 4 kilometers. So the one-way propagation delay denoted by tau is 4 kilometer, 4 times 1000 kilo, divided by the speed of the signal, 2 times 10^8. Why here is 2, not 3? Because the speed of the signal is the 2/3 of the light speed. So here is 2 times 10^8 meter per second. So the one-way propagation delay tau is 20 milliseconds. When station A and B transmit their frames almost at the same time, it takes the least time for station A to detect collision. The minimum period is tau is equal to 20 milliseconds. When the frame sent by station A is about to arrive but has not yet arrived at station B. About to arrive but has not yet arrived at. Nearly arrived at station B. Then B transmitted the frames. Or then at this time, station A detects the longest cognition time, which is too tall. That is too tall. That is 40 milliseconds. Why? For example, here is A, right? So A, then here is B, and we will draw the sequence chart. Then here is tall, right? It's tall. So tall. The first bit arrive at the station B. Then the propagation delay is tall. Then when station A and B transmit their frames almost at the same time, that means B almost at the same time start to transmit. So station A, it takes the least time. So at the time tau A, station A knows the cognition occurred. If the station B begin to arrive at this time point, that is when the frame sent by station A will arrive at this point, but about to arrive, not yet arrive at. So at this point, here, this gap is epsilon. Epsilon is larger than 0. Larger than 0. So at this condition, then it takes the longest cognition time, that is too tall. That is too tall for A to notice the cognition. So too tall is 40 milliseconds. Now, question 2. Consider a CSMA-CD LAN or Ethernet running at 100 megabps over a 1 kilometer cable. The signal speed in the cable is 200,000 kilometers per second. Okay, what is the minimum contention slot or contention period? What is the minimum frame size? Okay, signal propagation delay, tau, is L divided by V, right? It's this. The maximum contention period is too tall. Just now we have explained too tall, right? Too tall. Okay, here is a too tall. Okay, there is a question 2. If the distance between station A is shortened to 2 kilometers, what should the minimum frame size? Okay, then the new propagation delay, the tau prime, is 10 millisecond. Then L mean, the minimum frame length is 2 tau times data rate capital C, right? So we get 200 bits. It's very easy. So the maximum contention slot is 2 tau, so is 10 millisecond, right? The minimum frame size is F min or L min, or both okay. L min or FM is 2 tau times capital C, the data rate. So we get 1000 bit. It's easy, right? Question 3. CSMA-CD Ethernet data rate 1 gigabps. Signal propagation speed is 2 times 10⁵ kilometer per second. Here's kilo, so here 5. The length of the channel 200 meter. What is the minimum length of frame? Minimum length of frame 2 tau times C. Tau is L over V, right? So we get 2000 bits or 250 bytes. Okay, question 4 and 5, you can solve by yourself easily. It's very easy, right? Depend on, you can use this equation. F min is equals to 2 tau times C, right? It's very easy. So I will not introduce these questions in detail. So, and we will begin. Okay, new chapters and network layer. Network layer. Today we will begin to study chapter 5, the network layer. Last time we have finished the MAC layer. Network layer, we will focus on these 4 points. Network layer design issues, routing algorithm, internet working, the network layer in the internet. In this chapter, we will talk about IP protocol, IP packet format, IP address, IP routing. Okay, we will focus on 3 main questions. Format, packet format, address, routing. These 3 algorithms. So the network layer is concerned with getting packets from the source all the way to the destination. Getting to the destination may require making many hops at intermediate routers along the way. So probably many hops are needed. The network layer is the lowest layer that deals with end-to-end transmission. To achieve its goals, the network layer must know about the topology of the network. Topology means the set of all routers and links, and choose appropriate paths through it. Even for large networks, it must also take care when choosing routes to avoid overloading some of the communication lines and routers while leaving others idle. That is balance, traffic balance. So it must also take care of traffic balance. In this chapter, we will study all these issues and illustrate them, primarily using the Internet and its network layer protocol, IP. We will give an introduction to some of the issues that the designers of the network layer must grapple with. These issues include the service provided to the transport layer and the internal design of the network. So usually, the lower layers provide the services to the upper layers. So the transport layer is based on network layer. So transport layer uses services provided by the network there. Before starting to explain the details of the network there, it is worth restating the context in which the network layer protocols operate. This context can be seen in this figure. This figure illustrates the environment of network layer protocols. And we have two hosts denoted by host H1 and 2. And we have communication networks, and there are several routers, A, B, C, D, E, and F. They are routers. Okay? And these routers operated by Internet Service Provider, that is ISP, Internet Service Provider. So the over is called ISP's equipment. And the packets delivered, generated by host H1 are delivered along with the path, hop by hop, and arrive at H2 finally. So we noticed that when we standing on router A, we have two choices, to B and to C. So which one is better? And then we standing at D, probably we have two directions, to C and to E. So which one, which output interface should be selected? That is depend on the router algorithm, the routing algorithms. So the major components of the network are the ISP's equipment, routers connected by transmission lines. Transmission lines, usually we call them transmission links. So shown inside the shaded ovals, and the customer's equipment shown outside the ovals. So host H1 is directly connected to one of the ISP's routers. It's directly connected to the one router A. Perhaps at a home computer that is plugged into a DSL modem. In contrast, H2 connected to the internet with local area network, LAN. So usually H2 is a computer in the office, which might be an office Ethernet with a router F, owned and operated by the customer. Since F is outside of ISP's equipment, so router F is owned and operated by the customers, is the devices in the customer's office. It is not belong to the ISP. So this router has a needs the line to the ISP's equipment. We have shown F as being outside because that's not belong to ISP. So for the purposes of this chapter, however, routers on customers' premises are considered part of the ISP's network because they run the same algorithms as the ISP's routers. And our main concern here is the algorithms. And this equipment is used as follows. A host with a packet to send transmits it. A host with a packet to send transmits it to the nearest router. Host 1 transmits its packets to the nearest router. For this topology, there is only one choice, only one router connected to host 1, so delivered directly to router A. Right? So a host with a packet to send transmits it to the nearest router, either on its own LAN or over a point-to-point link to the ISP. The packet is stored there until it has fully arrived and the link has finished its processing by verifying the checksum. Then it is forwarded. The packet is forwarded to the next router, along the path. So a packet delivered to router A delivered to the next router, to C. So it is forwarded to the next router along the path until it reaches the destination host, where it is delivered. This mechanism is store and forward packet switching, as we have seen in the previous chapters. So this mechanism is called store and forward switching, hop by hop. The network layer provides services to the transport layer at the network layer transport layer interface. So network that provides services to the transport layer at the services between them. The important question is precisely what kind of services the network layer provides to the transport layer. The services need to be carefully designed with the following goals in mind. The services should be dependent of the router technology. The transport layer should be shielded from the number, type, and topology of the routers present. The third one is the network addresses made available to the transport layer should use a uniform numbering plan, even across local area network and WAN, wide area network. So the services needed to be carefully designed with the following goals in mind: service dependent. Transport layer should be shielded from the under characteristics. The network addresses should use a uniform numbering plan. Given these goals, the designers of the network layer have a lot of freedom in writing detailed specifications of the services to be offered to the transport layer. This freedom often degenerates into a raging battle between two warring factions. The discussion centers on whether the network layer should provide connection-oriented service or connectionless service. So there are discussions between the two camps. One camp, represented by Internet community, argues that the router's job is moving packets around and nothing else. So the Internet community argues that the router's job is moving packets as soon as possible. So nothing else. In this view, based on 40 years of experience with a real computer network, the network is inherently unreliable, no matter how it is designed. So in the view of real computer network, the network is inherently unreliable. Therefore, the hosts should accept this fact and do error control and flow control themselves. So this is the viewpoint of Internet community with the first camp. Then this viewpoint leads to the conclusion that the network service should be connectionless with primitives such as send packet and receive packet and neutral errors. In particular, no packet ordering and flow control should be done because the hosts are going to do that anyway, and there is usually little to be gained by doing it twice. This reasoning is an example of the end-to-end argument, a design principle that has been very influential in shaping the Internet. So this is the viewpoint from computer network. Furthermore, each packet must carry the full destination address because each packet sent is carried independently of its predecessors, if any. So what is the viewpoints? The network is unreliable. It is unnecessary to deal with ordering, flow control twice. Unnecessary. And each packet must carry the full destination address. This is the viewpoint of network. The other camp, represented by the telephone company, argues that the network should provide a reliable connection-oriented service. So they are fully different viewpoints. They are with fully different viewpoints. So they claimed that, the other camp claimed that 100 years of successful experience with the worldwide telephone system is an excellent guide. In this view, quality of service is the dominant factor. And without connections in the network, the quality of service is very difficult to achieve, especially for real-time traffic, such as voice and video. So the viewpoint of the telephone company argues that the network should provide should guarantee the quality of service. Quality of service, QS. So two different organizations are possible depending on the types of services offered. If connectionless service is offered, packets are injected into the network individually and routed independently of each other. No advanced setup is needed. In this context, the packets are frequently called datagram, and the network is called a datagram network. This is a connectionless service. The second type of service is connection-oriented service. If connection-oriented service is used, the path from the source router all the way to the destination router must be established before any data packets can be sent. This connection is called a virtual circuit, VC. In analog with the physical circuit set up by the telephone system, and the network is called the virtual circuit network. So if connectionless service, the packet called datagram, network called datagram network. If connection-oriented service is used, the connection called VC, the packet called also packet. The connection is called VC. The network is called VC network, virtual network. Let us now see how a datagram network works. Datagram networks, or what is a datagram network? Datagram means in this network, we use a connectionless service, right? And the packets routed independently of each other. No advanced setup is needed, and the packet carries the full destination address. Independently of each other, like this, illustrated by Figure 2, routing within a datagram network. We have host H1, host H2, and we have these routers denoted by A, B, C, D, E, and F. And we notice that the routing table of A the routing table of A initial routing table of A is like this. And then later changed to this one. And the C's table, original table, the C's table like this. And E, the table of router E is like this. So that means sometimes at the same time the router is A to C, but at the later probably a router directs a packet to B. So that is initially and the router. So from this figure, we know packets 1, 2, 3 are all carried along this path A, C, E, F. But later, the routing table changed. So the fourth packet 4, is delivered to B, carried along another path, because they are independent with each other. If the destination is F, right? Destination is F. Destination is F. So the next hop should take B. Should take B, right? Should take B. Later. If the destination address is F, so the next hop should take B here. Initially, the destination address F, so the next hop takes the C. That is why packet 3 take this path, packet 4 take another path. Okay, let's have a rest. Let's have a rest for 10 minutes. Let's have a rest for 10 minutes. Please keep connection. Please keep connection. Okay, let's continue. The next section we have look at talk about the figure 2. In the datagram network, the rotors are delivered independently with the full destination address, and depending on the current routing table, because the routing table probably will be updated, so the different routers probably delivered with different paths. Suppose that the process P1, the process is application process denoted by P1 in the H1, process 2 in host 2, host H2, and the process P1 has a long message for P2. It has the message to the transport layer. It has the message to the transport layer with instructions to deliver it to the process P2 on host H2. Let us assume for this example that the message is 4 times longer than the maximum packet size. So the network layer has to break it into 4 packets, 1, 2, 3, 4, and send each of them in turn to router A using some point-to-point protocol, for example, PPP, like this, PPP, like this. So break it into 4 packets, 1, 2, 3, and 4, and send each of them in turn to router A using some point-to-point protocol, for example, PPP. At this point, the ISP takes over. Every router has an internal table telling it where to send packets for each of the possible destination. This is possible destination. The second column means the next hop. So each table entry, means each table entry, the first entry, the second entry. Each table entry is a pair consisting of a destination and the outgoing line. Outgoing line, also called the next hop interface. Outgoing line to use for that destination. Only directly connected lines can be used. For example, in figure 2, A is self. B to B, the next hop. For A's table, if a packet arrives at A, the destination is B, so the next hop is to B. If the destination is C, so to the C. If the destination is D, to the B. If the destination is E, to the C. If the destination is F, to the C. That is what the routing table tell us. So A has only two outgoing lines to B and to C. So every incoming packet must be sent to one of these routers, even if the ultimate destination is to some other routers. A's initial routing table is shown in the figure under the label initially. At A, packet 1, 2, and 3 are stored briefly, and having arrived there on the incoming link and had their checksums verified, then each packet is forwarded according to A's table onto the outgoing link to C within a new frame. Packet 1 is then forwarded to E and then to F. When it gets to F, it is sent within a frame over the local area network to H2. Packet 2 and 3 follow the same routes. So, however, something different happens to packet 4. What difference happens? When it gets to A, it is sent to route B, even though it is also destined for F. For some reason, A decided to send packet 4 via a different route than that of the first 3 packets. Why? Because the routing table has changed at that time. So perhaps it has learned of a traffic jam somewhere along the path ACE and updated its routing table as shown under the label later. So the algorithm that manages the tables and makes the routing decisions is called the routing algorithm. So routing algorithm we will talk about in detail in the later sections. IP. Well, the concept of IP we will talk about in detail, which is the basis for the entire internet. It's the dominant example of a connectionless network service. Each packet carries a destination IP address that rows used to individually forward each packet. The addresses are 32 bits in IPv4 packets and 128 bits in IPv6 packets. It's the address. Just now we mentioned routing algorithm. Here, addresses. Then we will talk about packet format. For connection-oriented service, we need a virtual circuit network. Let's see how that works. When a connection is established, a route from the source machine to the destination machine is chosen as part of the connection setup and stored in tables inside the routers. That route is used for all traffic flowing over the connection, exactly the same way that the telephone system works. When the connection is released, the virtual circuit is also terminated. When the connection-oriented service, with connection-oriented service, each packet carries an identifier telling which virtual circuit it belongs to. So for the connection-oriented service, it will use a fairly different routing mechanisms, fairly different. different to the connectionless service. So Figure 3 shows the routing within a connection-oriented network that with virtual circuit. An example considered the situation in Figure 3. So we have host 1, host H1, H2, H3 in the topology, and we have the router denoted by A, B, C, D, E, F. And the original large message divided into 4 packets. Packet 1, 2, 3, and 4. And for the router A, have A's routing table with virtual circuit. For the router C, has this routing table. The E have this routing table. The routing table is different from the connectionless service. So H1 means the source address. So H1, if router A received or a packet delivered by H1 arrives at A will select will select the virtual circuit 1. So it will deliver to C. Okay. Here, host H1 has established connection 1 with host H2. This connection is remembered as the first entry in each of the routing tables. The first line of A's table says that if a packet bearing connection identifier 1 comes in from H1 with a VC1 from H1, if the first line of A's table says if a packet bearing connection identifier 1 comes in from H1, it is to be sent to router C and given connection identifier 1 to C and given identifier 1. If identifier 1 with identifier 1 from H3 will forwarded to C and gives identifier 2. So similarly, the first entry at C routes the packet to E, also with a connection identifier 1. C from A to the E gives identifier 1. packets with identifier 1 from A delivered to E and gives an identifier 2. So now let's consider what happens if host H3 also wants to establish a connection to H2. It chooses connection identifier 1 and tells the network to establish the virtual circuit. This leads to the second rule in the table. Note that we have a conflict here because although A can easily distinguish connection 1 packets from H1, from connection 1 packets from H3. Okay, a packet from H1, a packet from H to H3. Here, distinguish the connection 1 packets from H1 from connection 1 packets from H3. So here we have 3 froms. C cannot do this. For this reason, A assigns a different connection identifier to the outgoing traffic for the second connection. Avoiding conflicts of this kind is why routers need the ability to replace connection identifiers in outgoing packets. In some contexts, this process is called neighbor switching. An example of a connection-oriented network service is MPLS, multi-protocol neighbor switching. Comparison of virtual circuit and datagram network. Both virtual circuits and datagrams have their supporters and their detractors. We will now attempt to summarize both sets of arguments. The major issues are listed in Figure 4. Issues, here we listed issues, for example, circuit setup, addressing, state information, routing, effect of router failures, quality of service, and congestion control. For circuit setup, datagram network not needed. A virtual circuit network require circuit setup. Addressing datagram network. For datagram network, each packet contains the 4 source and destination addresses. For virtual circuit network, each packet contains a short VC number like this. VC number, short VC number. 1, 2, 3, this kind of number, VC number. State information. For datagram network, routers does not hold state information about connections. For virtual circuit network, each VC requires router table space per connection. Routing mechanisms. For datagram network, each packet is routed independently. For virtual circuit network, route chosen when virtual circuit is set up. All packets follow it. for the same path. Next issue is effect of router failures. Datagram network, none except for packets lost during the crash of routers. Virtual circuit network, all virtual circuit that passed through the failed router are terminated. So the effect of router failures is serious for virtual circuit network, but not serious for datagram network, because the datagram network can change the routing for the later packets. The quantity of service difficult for datagram network, but easy if enough resources can be allocated in advance for each VC. Quantity of service. Congestion control. Datagram network is difficult. So quantity of service and datagram are both difficult for datagram network, but easy for virtual circuit network. So datagram, we cannot easily decide which one is better, which one is the best, because datagram has some advantages, but the virtual circuit network has the other disadvantages. Inside the network, several trade-offs exist between virtual circuit and datagrams. So there's several trade-offs. One trade-off is setup time versus address passing time. Setup time and address passing time. Using virtual circuit requires a setup fees, which takes time and consumes resources. However, once this price is paid, figuring out what to do with a data packet in the virtual circuit network is easy. The router just uses the circuit number to index into a table to find out where the packet goes in the datagram network. No setup is needed, but a more complicated lookup procedure is required to locate the entry for the destination. A related issue is that the destination addresses used in the datagram networks are longer than circuit numbers used in virtual circuit networks because they have a global meaning. Which one has global meaning? Which one is global meaning? The refers who? Which one has global meaning? Datagram or the address in datagram or virtual circuit? Which one has global meaning? Here the refers the destination address used in datagram network, right? The destination addresses used in datagram network are longer than circuit number used in virtual circuit because they have global meaning. That means the destination address used in datagram network has a global meaning. So the global meaning probably is longer. Local meaning probably is shorter. So it's a global meaning versus local meaning. Yet another issue is the amount of table space required in rotor memory. Rotor memory. A datagram network needs to have an entry for every possible destination, whereas a virtual circuit network just needs an entry for each virtual circuit. A virtual circuit has some advantages in guaranteeing quantity of service and avoiding congestion within the network because resources can be reserved in advance. When the connection is established. When a datagram network, congestion avoidance is more difficult. So why for virtual circuit, quantity of service and avoiding congestion is more easier. It's more easier because resources can be reserved in advance for virtual circuit. When connection is established. But for datagram network, congestion avoidance is more difficult. For transaction processing systems, for example, stores calling up to verify credit card purchases, the overhead required to set up and clear a virtual circuit may easily dwarf the use of the circuit. On the other hand, for long-running uses such as a VPN traffic between two corporate offices, permanent virtual circuit may be useful. So that means sometimes we need datagram network, sometimes we need virtual circuit. For example, usually VPN traffic, permanent virtual circuit that are set up manually and last for months and years. Especially you can apply the broadband access for months or years. Virtual circuits also have a vulnerability problem. If a router crashes and loses its memory, even if it comes back up a second later, or the virtual circuit passing through it will have to be aborted In contrast, if a datagram router goes down, only those users whose packets were queued in the router at the time need suffer. The loss of a communication line is fatal to virtual circuit using it, but can easily be compensated for if datagrams are used. So, which one is better? Virtual circuit may suffer the router failure seriously, but datagram it can easily be compensated for. The main function of the network layer. The main function of the network layer. What is the main function of network layer? Is routing packets from the source machine to the destination machine. In most networks, packets will require multiple hops to make the journey. Make the journey means being delivered hop by hop and finally arrive at the destination. Make the journey along, transmitted along the path. The algorithms that choose the routes and the data structures that they use are a major area of network layer design. The routing algorithm is that part of the network layer software responsible for deciding which output line an incoming packet should be transmitted on. If the network uses datagrams internally, this decision must be made anew for every arriving data packet, since the best route may have changed since last time. If the network uses virtual circuit internally, routing decisions are made only when new virtual circuit is being set up. It is sometimes called session routing. So routing algorithm is that part of network layer software responsible for deciding the path, deciding which output lines an incoming packet should be transmitted on. It is sometimes useful to make a distinction between routing and forwarding. One can think of a router as having two processes inside it. Which two processes? Routing processes and forwarding processes in the routers. Routing process is responsible for filling in and updating the routing table. So routing processes is maintain the routing table, filling in and updating the routing table. The second component is forwarding process. Forwarding process means handle each packet as it arrives, looking up the outgoing line and to use for it in the routing table. So routing process, updating the routing table, and the forwarding process use the routing table and forward each packet. with the routing information, right? Okay. Certain properties are desirable in the routing algorithm. Properties are desirable. So what properties are desirable in routing algorithm? The first one is connectedness. So routing algorithm results should be correct. The packet should be delivered finally to the destination. So should be correct. Routing should be correct. Then the second should be simple. Simplicity. So the routing process should be simple. Should be with high efficiency. Right? Simple means high efficiency. The simplicity. Robustness. Robustness means stable. In the various conditions, robust. The stability means so they are sometimes some same. Okay. Stability. Fearless. Fearless means the routing provides fair services for different packets. Fearless. And efficiency. Efficiency probably related to simplicity. Robustness probably related to stability. Connectedness is the first one. Okay. Once a major network comes on the air, it may be expected to run continuously for years without system-wide failure. The routing algorithm should be able to cope with changes in topology and traffic without requiring all jobs in all hosts to be aborted. A stable algorithm reaches equilibrium and stays there. It should converge quickly too. Fearless efficiency may sound obvious, but as it turns out, they are often contradictory goods. Before we can even attempt to find trade-offs between fairness and efficiency, we must decide what it is we seek to optimize. Minimizing the mean packet delay. The mean packet delay is an obvious candidate to send traffic through network effectively, but so is maximizing total network throughput. As a compromise, many networks attempt to minimize the distance a packet must travel, or simply reduce the number of hops a packet must make. So, certain properties desirable in the routing algorithms. So when designing routing algorithm, these properties or these goals should keep them in mind. Routing algorithm can be grouped into two major classes, non-adaptive and adaptive. So much for today, and we will talk about the the other properties of routing algorithms next time. Bye.